Hey, what's up everybody? It's your boy Mac, welcome back. Today, we're diving into something that's literally cool. It's all around us, happening in ways you might not even realize. From the air we breathe to the deepest reaches of space. We're talking about the Joule Thomson effect. Now, consider this. The Joule Thomson effect describes how the temperature of a real gas, not an ideal one, but the real stuff, changes when it expands without exchanging heat with its surroundings. It's like letting a gas stretch out, take a deep breath, and in doing so, it either cools down or sometimes heats up. It's all about pressure, temperature, and the tiny forces between molecules. This isn't just some abstract concept from a dusty old textbook. No, this is science in action, the engine behind so much of our modern world. Think about it. The Joule Thomson effect is the scientific principle that makes so many things possible. It's in the refrigerators that keep our food fresh, the air conditioners that keep us comfortable on a hot day, and even in the technology that lets us explore the universe. It's a fundamental piece of thermodynamics that has been harnessed for countless practical applications, turning a simple observation about gas behavior into a powerful tool for innovation. So, stick with me. We're going to break it down, explore how this amazing effect works, and see where it shows up in our lives. From giant industrial plants to tiny sensors, the Joule Thomson effect is a silent hero working behind the scenes. We're going to look at 10 incredible applications that show just how important this little bit of physics truly is. It's going to be an enlightening journey, a real trip. So let's get into it. Bill, let's go. All right, first up, gas liquefaction plants. These are massive, incredible facilities. Think of them as giant factories that take the air all around us and separate it into its core components. We're talking about pure oxygen, nitrogen, and argon. How do they do it? You guessed it. The Joule Thomson effect is the star of the show. Inside these plants, they use something called an air separation unit. They take regular air, compress it to a super high pressure, and then cool it down. This high-pressure, pre-cooled air is then forced through a valve, causing it to expand rapidly. This expansion is where the magic happens. As the gas molecules spread out, they have to work against those tiny attractive forces holding them together, the van der Waals forces. That work uses up energy, and that energy comes from the gas itself, causing its temperature to plummet. It gets colder and colder with each cycle of compression and expansion. Eventually, the air gets so cold that it turns from a gas into a liquid. From there, they can separate the liquid oxygen, nitrogen, and argon through distillation. It's a beautiful, elegant process, all powered by this fundamental principle of thermodynamics. Next, let's get even colder and talk about cryogenics. The word itself sounds like something out of science fiction, but it's a very real and very important field of science. Cryogenics is the study of producing and behaving of materials at extremely low temperatures. We're talking temperatures approaching absolute zero. And the Joule Thomson effect is a key player in reaching these frosty depths. To achieve these ultra-low temperatures, scientists need to liquefy gases like helium and hydrogen, which have incredibly low boiling points. The JT effect is essential for that final push into the cryogenic realm. Once you have these cryogenic fluids, you can do some amazing things. You can preserve biological samples like stem cells or tissues for long-term storage, essentially pausing time for them. In research, cryogenic environments are used to simulate the cold, empty conditions of outer space, allowing us to test equipment destined for satellites and probes, and it's crucial for superconductors, materials that conduct electricity with zero resistance, but only work when they're kept incredibly cold. The Joule Thomson effect provides the cooling power needed to unlock these extraordinary properties, pushing the boundaries of what's possible in medicine, physics, and exploration. Now let's bring it back home to our kitchens and our living rooms. We're talking about refrigeration and cooling systems. That cold air coming from your fridge or AC unit, you can thank the Joule Thomson effect for that. Many cooling systems, especially large-scale industrial ones, are based on cycles that rely heavily on JT expansion. Two of the most famous are the Lindy cycle and the Claude cycle. The Lindy cycle is a classic example. It compresses a gas, cools it, and then expands it through a JT valve to produce a significant temperature drop. Part of the gas liquefies, and the rest is cycled back to help cool the incoming compressed gas. This process is incredibly efficient and is the backbone of many refrigeration technologies. It's not just for home appliances, it's used on a massive scale. For example, liquefying natural gas, or LNG, is a huge industry. To transport natural gas across oceans, it's cooled to about -162 degrees Celsius, which turns it into a liquid and shrinks its volume by 600 times. This is achieved using sophisticated multi-stage cooling cycles where the Joule Thomson effect is a critical step. The same goes for liquefying helium, the coldest of all gases, for use in things like MRI machines. It's all about harnessing that expansion to pull heat out of the system. Let's head out to the oil and gas fields. When natural gas comes out of the ground, it's not just pure methane. It's actually a mix of different hydrocarbons, water vapor, and other impurities. Before it can be put into the pipeline and sent to our homes, it has to be processed and cleaned up. One of the most important steps is controlling the dew point. That's the temperature at which liquids like water and heavier hydrocarbons will start to condense out of the gas. If these liquids form in the pipeline, they can cause corrosion, blockages, and, well, all sorts of problems. This is where the Joule Thomson effect comes in as a simple yet brilliant tool. To control the dew point, processing plants use something called a Joule Thomson valve, or a JT skid. They take the high-pressure gas straight from the well and pass it through this valve. The pressure drops dramatically on the other side, causing the gas to expand and cool down significantly due to the JT effect. This sudden cooling forces the water vapor and heavier hydrocarbons, known as natural gas liquids or NGLs, to condense into liquids. These liquids can then be easily separated from the main methane gas stream. It's an elegant, passive way to purify the gas and recover valuable NGLs like propane and butane, all without any complex machinery, just pure physics. Now, not all gases are created equal when it comes to the Joule Thomson effect. Most gases, like nitrogen or carbon dioxide, cool down when they expand at room temperature. But two very important gases, hydrogen and helium, actually do the opposite. They heat up. This is because they have very, very low inversion temperatures. The inversion temperature is the critical point above which a gas will warm upon expansion, and below which it will cool. For hydrogen, that temperature is about -80 degrees Celsius, or 202 Kelvin, and for helium, it's an incredibly cold -240 degrees Celsius, or 40 Kelvin. So if you just expand hydrogen or helium at room temperature, they get warmer, not colder. To use the Joule Thomson effect to liquefy them, you have to be clever. You need a multi-stage cooling process. First, you have to pre-cool the gas using other methods like liquid nitrogen to get its temperature below its inversion point. Only then can you use JT expansion for that final, deep cooling phase to turn it into a liquid. Often this is done using the Claude cycle, which combines JT expansion with an expansion turbine that does work, providing a more efficient way to cool these tricky gases. It's a great example of how scientists have to layer different principles to solve tough engineering challenges. Have you ever used a can of compressed air to clean your keyboard and noticed how cold the can gets? Or seen the frost that forms on the valve of a CO2 fire extinguisher when it's used? That's the Joule Thomson effect in action, right in your hands. When you release a gas from a high-pressure cylinder, it expands very quickly as it exits the nozzle. This rapid expansion causes a significant drop in temperature. The gas leaving the cylinder is suddenly at a much lower pressure, so it cools down, and that cooling effect is transferred back to the cylinder and the valve. This phenomenon isn't just a neat party trick, it's a critical consideration in safety engineering. Engineers who design high-pressure gas systems have to account for this cooling. If the temperature drops too much, it can make the metal of the cylinder or the valve brittle and prone to fracture, which could be catastrophic. It can also cause moisture in the air to freeze, potentially blocking the valve or regulator. So, materials are carefully chosen, and systems are designed to withstand these rapid temperature changes, ensuring that high-pressure gases can be stored and used safely. It's a reminder that even simple physics can have major safety implications. Let's talk about seeing things that are, well, invisible to the naked eye. I'm talking about thermal imaging and night vision. Many of the most sensitive infrared detectors, the very sensors that let us see heat signatures, actually need to be extremely cold to work properly. So why is that? Well, it's because everything emits thermal radiation, including the detector itself. If the detector is warm, its own heat noise will totally overwhelm the faint infrared signal it's trying to capture. To get a clear picture, you have to cool the sensor down to cryogenic temperatures. And you might be wondering, how do you achieve that in a compact portable device like a night vision scope or a thermal camera? You use a miniature cryocooler, and honestly, many of these tiny refrigerators rely on the Joule Thomson effect. They use a small compressor to pressurize a gas like nitrogen or argon, and then expand it through a tiny microscopic JT orifice right at the back of the sensor. This creates a spot of intense cold that keeps the detector at its optimal operating temperature. It's really an incredible feat of microengineering, packing a powerful refrigeration cycle into a device that can fit in your hand, all to give us the superpower of seeing in the dark. From the palm of your hand, let's go to the vastness of space. When we send telescopes and scientific instruments into orbit to observe the universe, they often face the same problem as the thermal cameras we just talked about, but on a much grander scale. To detect the faint infrared light from distant stars, galaxies, and nebulae, the detectors on telescopes like the James Webb Space Telescope need to be incredibly cold. Any heat from the instrument itself would blind it to the cosmic signals it's trying to see. The challenge is, how do you keep something cold in space, where you're constantly bombarded by sunlight? You use sophisticated cooling systems, and once again, Joule Thomson coolers are often part of the solution. For instruments that need to reach the lowest possible temperatures, a JT cooler can provide that final stage of deep cooling. Satellites can carry tanks of high-pressure gas, like nitrogen or helium, and use a JT expansion valve to create a reliable, vibration-free source of cryogenic cooling. This is crucial because even the tiniest vibration from a mechanical cooler could shake the telescope and blur the images. The Joule Thomson effect provides a silent, steady way to maintain the frigid temperatures needed to unveil the secrets of the cosmos. Okay, let's come back down to Earth and look at a very practical, industrial process bottling gases. When companies fill cylinders with gases like oxygen, nitrogen, or argon, they are taking a huge volume of gas and compressing it into a small, strong steel container. This process involves big changes in pressure. We already know that when gas expands, it cools down. The reverse is also true. When you compress a gas rapidly, it heats up. However, the process of filling a cylinder is a bit more complex, and the Joule Thomson effect still plays a role, especially during depressurization or transfer. Engineers have to carefully manage temperatures during the filling and emptying of these cylinders. If a cylinder is filled too quickly, the gas inside can get very hot. Conversely, if gas is transferred from a large storage tank to a smaller cylinder, the expansion that occurs as it enters the lower pressure cylinder can cause significant cooling. This JT cooling needs to be managed to prevent the temperature from dropping so low that it causes condensation of the gas, or, in the case of gas mixtures, causes one component to liquefy before another. It's a delicate balancing act of pressure and temperature to ensure the gas is bottled safely and remains in its desired gaseous state. For our final application, let's look at something that's fundamental to all of science measurement. How do you know your thermometer is accurate, especially when you're measuring very low temperatures? You need to calibrate it against a known stable temperature standard. But how do you create a perfectly stable, ultra-low temperature on demand? The Joule Thomson effect provides an elegant way to do just that. By carefully controlling the expansion of a gas, you can create a specific, constant, and reproducible low temperature. In calibration labs, scientists can build an apparatus where a gas like nitrogen or argon flows at a constant pressure and then expands through a JT valve. This expansion produces a steady stream of two-phase fluid, a mix of liquid and vapor, at a very precise temperature, which is the boiling point of that fluid at that specific pressure. By placing the thermometer or sensor that needs to be calibrated into this stable, low-temperature environment, they can check its accuracy and make any necessary adjustments. It's a way of using a fundamental physical effect to create a benchmark, a standard of cold, which underpins the accuracy of countless other scientific experiments and industrial processes. So there you have it. 10 incredible, diverse applications all powered by one fundamental principle, the Joule Thomson effect. From liquefying the air we breathe and keeping our food fresh, to helping us peer into the darkest corners of the universe and see in the dark, this effect is a true cornerstone of modern technology. It's a perfect example of how a deep understanding of the physical world, of the way tiny, invisible molecules interact, can be harnessed to build amazing things. It's not just abstract science, it's the engine of innovation that quietly hums in the background of our lives. The world is a complex, beautiful, and interconnected place. The same physics that makes a can of compressed air feel cold is the same physics that allows a space telescope to capture images of galaxies billions of light years away. It's a reminder that the principles of science are universal, and they pop up in the most unexpected places. The next time you open your refrigerator, see a fire extinguisher, or just feel a cool breeze, take a second. Think about the incredible dance of pressure, temperature, and energy that's happening all around you all the time. I encourage you to keep your eyes open, to stay curious. Look for these connections. Science isn't just something that happens in a lab. It's everywhere. It's in the kitchen, in the sky, in the machines we use every day. Thanks for hanging out and exploring this with me. It's been real. Until next time, stay cool and keep wondering. Peace.